Hey guys, so at this point in the class, we've been studying forces for most of the time, and we're starting to now talk about energy. And so I'd like to just talk a little bit about how I believe that energy is a more intuitive concept than the forces that we've been studying so far. And of course, physics is supposed to describe the real world, and the real world we see around us. This is intuitive naturally because we have experience with it. So we want to connect what we do in the physics classroom with what happens in the real world as much as possible. So forces seem like they would be intuitive, right? I push on something and it moves. That's a pretty intuitive idea, but in order to convert that from that concept into prediction, say, for the velocity or the position of an object, we have to do Newton's second law. So we have to do the free body diagram, figure out what all the forces are, do Newton's second law, find the acceleration, and then only through the kinematic equations can we use the acceleration. The acceleration itself is not a very intuitive concept, and that's sort of the problem with the connection between intuitive things like forces and intuitive things like positions. You have to go through the acceleration. The work energy theorem, which is what we're studying now, which is the first part of energy, is much more intuitive idea because it deals with how much work you do on an object. That gives an object a kinetic energy, and kinetic energy is velocity. So it's much more natural to think of, I have a block, I do some work on the block, that makes the block move, gives it a kinetic energy. What is the velocity that corresponds to that kinetic energy? So there's a much more direct connection there between how much work I do on an object and how fast that object is moving. Now, of course, we have to use this thing called energy, but energy is sort of an intuitive idea too. You know, if I'm jumping up and down and running all over the place, I have a lot of that energy. If I pull on a spring, for instance, that has a lot of energy because it's hard for me to keep it stable. So energy is actually a pretty intuitive concept, although it's difficult to define explicitly. But I hope that by looking at this work energy stuff, you'll get a better idea about how the real world is working from a more intuitive standpoint than the forces acceleration stuff, which can be a little bit confusing as we've seen. So that's what I hope to sort of convince you of in this video.
So the example I want to do to convince you of the intuitive nature of the work energy theorem is the following. You have a hockey puck being pushed on the ice by a hockey stick with a force Fp over a distance d. So this is like when you're shooting the puck with the stick, you act over a very short distance with some constant force Fp. So previously, what we would have to do this problem is start with the free body diagram, do Newton's second law, then find the acceleration, then do the kinematic equations. But now we have a slightly more direct way of figuring out how fast this thing is moving. So start with a picture, of course. You're never going to get away from pictures in physics. And we want to use work energy. So the book writes the work energy theorem is this. I might write this work external as the net work. But however you write it, the change in the kinetic energy has to be due to all the work acting on the object. In other words, you cannot write something along the lines of the change in kinetic energy is equal to the work due to friction. Right? That is not right, particularly, unless friction is the only force acting on it. But in most cases, that's not true. So this external work that the textbook calls this thing, that has to be all the things that are making the object have some kinetic energy. Okay, so we write down the definition of the change in kinetic energy. That's just the final kinetic energy minus the initial kinetic energy. 1/2 mv squared minus 1/2 mvi squared. Here the initial velocity is going to be 0. I'll put that in later. So now I want to write down the total external work. I'll write F net times d because I really do want the net force on this hockey puck, and of course that is just going to be Fp times the distance over the hockey puck is acting. So combining these two, we get that. And now I'll put in the fact that the initial velocity here is 0. And now we just have a simple relationship between the final velocity, which is what we want to find, and the force that we push on. And with some algebra we can get the final answer, which is just the square root of 2fp d over m. So when I say that this is an intuitive approach, I don't obviously mean that this answer is intuitive. There's no way that without doing exactly this, you would have come up with the square root of 2fp d over m as the right answer. What I mean is intuitive is the following. Consider now that the ice is not totally frictionless. The ice has some small amount of friction. If you were going to put that in here, you'd have to go back to the free body diagram, put the friction on, get a different Newton's second law, get a different acceleration, and then redo the kinematic equations. But here what we're doing is we're just having a different net force. I mean, we're just having a force of friction, which is pushing backwards right there. So what's that doing? That's just reducing the net force on the object, and it's just changing this thing right here. So in fact, we can just replace our Fp in there with Fp minus Ff. Why? Because this force is now smaller. It's smaller due to the friction. So now we can just rewrite the final answer immediately. Is now 2 times Fp minus Ff, the difference between the forces, times d over m. And so to me this approach is more intuitive because what are we doing? We're just changing this force, and this explicitly says, oh, how does this force change? It changes by some amount due to the friction, and you get a new velocity out of it.
So one last quick thing I want to mention about this is that in all this analysis, you notice that I didn't use any vectors at all. This was all scalar stuff. So that is something which should stick in your head and go, oh, great, I don't have to use vectors anymore. So that's not exactly true, but these are generally scalar equations, not vectors. And so in the next video, which I hope you're going to watch right after this one, I'm going to talk a little bit more about that so you understand what it means exactly. All right, thanks, guys.